Okay, this is part 2, unit 10A. We're looking at fundamentals of geometry, and we're going to be looking at plane geometry. And again, we're talking plane, we're talking in a two-dimensional surface, so two-dimensional objects. So some of the most common are circles and polygons. And when we look at the definition of a circle, all points on a circle are located the same distance, radius, from the circle's center. So once you identify the center, no matter which direction you go in, which we call the radius, if you go equal distance, that is a terrible circle, but that's how you define a circle. It's all the points that are equal distance from a center point, and that distance is the radius. Okay, the diameter is twice as long as the radius, which means the diameter goes across the circle and passes through its center. So that's the key thing for the diameter, is it always has to pass through the center there. Now when we look at a polygon is any closed shape on the plane that's made from straight line segments. Okay, the root poly just means many, so a polygon is a many-sided figure. So, and these things don't have to be beautiful. I mean, you could just take and draw any straight lines you want, and this right here would be a polygon. But the polygons that you may be used to are what are called regular polygons, and this is where all the sides have the same length and all the interior angles are the same. So you can look at those in your textbook, table 10.1. But one polygon that's used very often, 3 sides is an equilateral triangle. Assume that those are all the same length. Also, you can go with a square, 4 sides of equal length. Again, we'll just assume that these are all equal length. And then you can go 5 sides, which is a pentagon, 6 sides, which is a hexagon, and so forth. Probably the most familiar for a lot of us is the octagon, which is a stop sign. But that's, again, a regular polygon is where all the side lengths are the exact same length. But those aren't the only polygons you run into. So a polygon can be any shape drawn with straight lines, but a regular polygon is where those side lengths are all the same and the interior angles are the same as well. Now when we're looking in 2 dimensions, and we have our objects, a couple of things that we measure. We can measure the perimeter, or kind of the outside length. So actually that is kind of a one-dimensional thing when we're just measuring a perimeter. If we jump up into 2 dimensions, then we have the area, and here are several different objects that are familiar, that have been used frequently, and just the formulas of finding the perimeter and the area. But again, just remember, perimeter is a length, so this is kind of in 1 dimension, so 1D, and the area, the area is, it is an area, but we'll just say that's a 2-dimensional object because you're trying to measure a plane surface, whereas the perimeter, you could take the perimeter, so say for example you have the circumference of the circle. If you were to pick this point and kind of make a slice right here and unravel the circle, then you have the point, and then it would extend out as a line segment. And so really, when I'm looking at perimeter, you're just looking at length. Oh, excuse me. So we're going to look at circles here. We're going to find the circumference and area of each circle and round to the nearest tenth. So remember that the circumference of the circle is either pi times the diameter or 2 times pi times the radius, because 2 times the radius is the diameter. So it depends on what you're given, but both are equivalent. So if we have a circle of radius 6 meters, then the circumference is going to be 2 times pi times 6, which would be 12 pi meters. And that is approximately, if I type it into a calculator, 37.7 meters would be the the circumference. So that's measuring around the outside or the exterior of the circle. And that's actually, again, if you're using that, your circumference, that's actually how your car measures the miles traveled. Is it takes, imagine a point there, it looks at the number of revolutions that your tire makes and multiplies it by the basically the circumference, and that's how it determines how much your car is traveling. So if you slap huge tires or really small tires on your car and you don't recalibrate the odometer, it actually could be a little bit off. Just an interesting thought there. Okay, next we're looking at the area. Area for a circle is always pi times the radius squared. And in this case, you do pi times 6 squared. So 6 squared is 36, so I'd write this as 36 pi. And that is, again, I should say approximately 113.1. And now we're in 2 dimensions, so that's going to be meters squared, or square meters. Okay, so that exponent, so this is meters to the first, also helps us see our dimension. Okay, next, if we have a radius of 8.2, so even if you throw a decimal in there, again, every calculation follows the same. Circumference 2 pi times the radius. And so if I multiply that out, get approximately 51.5 meters. Again, that's in 1 dimension, the length. The area, pi times the radius squared, and the radius is 8.2 squared. So this comes out to be 211.2 approximately meters squared, though, because remember, area is always squared because we're in 2 dimensions there. Okay, this next question is looking at this figure 10.14 and building a staircase. And so if you look in the textbook, you can get the context of figure 10.14. But suppose that the stairs rise at a steeper angle and are 11 feet tall. So instead of 9 feet here, these stairs are going to be 11 feet tall now. What is the area of the region to be covered in this case? So basically you need to figure out, well, it's not going to be straight yet, but what's going to be the area you would need here as far as like plywood to cover up the bottom of that staircase. And when you're finding the area of a triangle, it's 1/2 the base times the height. And we can assume that these stairs are built square, so that's going to be a right angle. So then you say 1/2 the base is 12 feet and the height is 11 feet. And so this is going to be 1/2 times 12 is 6 times 11 is 66. And this is going to be an area, so we're 2 dimensions, feet squared, or square feet. So again, just remember when we're in area, our dimensions are 2. When we're looking at a length or a perimeter, circumference, those type of things, we are in a single dimension or 1 dimension. Now, when you get into 3-dimensional geometry, there are 2 critical things that we'll look at in this unit, and that is the volume. And basically, if you think of volume, it's if you have a cup, the volume is how much of a liquid can you put inside of this thing. And then the surface area is just the area of the exterior of the surface, or of the figure that you're looking at. And so here are several, 10.3 gives us the name of several familiar 3-dimensional objects along with the formulas for volume and surface area. Now if you think about volume, so volume for a box or a cube is length times width times height. And again, there's 3 dimensions. We need a length, a width, and a height. And so that's going to be units to the 3rd power. So we're going to be like cubic meters or cubic feet or cubic centimeters or something like that. A surface area for a box or a cube or anything else is the result of just adding the areas. In this case of a box, it'd be adding the areas of 6 different sides or faces of the object. So if you have a cube here, you have 1 surface, you have 2 surfaces, you have 3 surfaces, and then 4 is going to be on this side, 5 is going to be on the bottom, and 6 is going to be this back side. So the surface area is just what's the area of all the surfaces combined on an object. Just checking my time here. And so again, when you're looking at surface area, so that word area, that's 2-dimensional. When you're looking at volume, we are in 3 dimensions. Now there are some what we call scaling laws, because a lot of these objects will build on a small scale or a model scale before we actually build the object itself. So in 3B, we looked at scaling as a process by which a real object is modeled by a similar object with whose dimensions are proportionally larger or smaller. So for example, an architect might make a scale model of an auditorium in which all the lengths are smaller by a factor of 100. Because if you want to model, you're going to want to scale that thing down so you don't have to build the actual thing, and it's much more cost effective, and then you can look at it and make some tweaks if needs be. Or a biologist might make a scale model of a cell in which all the lengths are larger by a factor of 10,000 because the cell is so small. Suppose that you were engineering a model of a car and you had a scale factor of 10. This means that the actual car is 10 times longer than the the actual car is 10 times as long as the model. It's also going to be 10 times as wide, 10 times as tall as your model car. So then the question becomes, well, how are the surface area and the volume of the actual car related to the surface area and the volume of the model? So let's consider one example here. So the area of the car's roof is what we're going to be looking at. So the area is just going to be the length times the width. Assume kind of a square top here. Because the length and the width of the actual car roof are each 10 times their size in the model, the area of the actual car roof will be found by the following. So the area of the actual roof area is going to be the actual length times the actual roof width. And we know that the model is, where the actual car is 10 times larger than the model, so you would take 10, multiply it by the model length, and then 10 times the model's width. And so we actually get 10 squared times the model length times the model width, or 10 squared times the area of the model's roof. So when we're scaling up areas, we take whatever that scale factor is and we're raising it to a second power. So our scale factor, 10 to the second, is 100 in this case when we're looking at the area. If we were to be looking at length, then it would be 10 to the first. If we're looking at volume of something, it would be 10 to the third. So it's all dependent upon those different dimensions that we are looking at. So you take the model scale factor, and it's going to be raised to a power of 1, 2, or 3, depending upon how big or how many dimensions we are looking at. Okay, so again, if you're looking at volume, you would take 10 to the third times it by your model volume if your scale is by a factor of 10. So here's just a couple of things about scaling laws. Length scales with the scale factor. So the lengths are kind of a 1-to-1 to the first power. Areas, they are the square of the scale factor. Volumes are the cube of the scale factor. And then just some things to keep in mind. If you're looking at surface area to volume ratio, you just take surface area divided by volume. And again, the surface area is to the second power, the volume is to the third power, so it turns out to be just 1 divided by that scale factor when you're looking at that ratio. So this will end part 2, and then we'll got a couple questions to cover in part 3.